Okay, hey everybody, this is the third video on enzymes and energy, and I just want to finish up those last couple of slides, talk a little bit about the demonstration. But first, I wanted to talk a little bit about the mechanisms that uh, the enzyme uses to lower activation energy. There are really four mechanisms, and I'd like to talk about each of them. So the first is like if the enzyme is joining two things, say, if the enzyme will grab onto those two reactants and hold them in the proper orientation, that's going to lower the activation energy. Remember that these things are moving around the milieu by Brownian motion, and so the chance of them colliding with each other is lower if you're not holding them next to each other in the proper orientation. And so if an enzyme does that, holds the reactants near each other, then that will lower the activation energy. The second way is that induced fit we talked about. When the substrate enters into the active site, we have an induced fit due to the binding of the enzyme and substrate into the enzyme substrate complex. And that binding changes the shape of the enzyme. And that change of shape of the enzyme changes the shape of the substrate. And that change of shape, the new shape more closely resembles the transition state. And so that's going to be really important because it's going to stress certain bonds, maybe that you need to cut or redistribute electrons, this sort of thing. Um, the last two have to do with the R groups that are in the active site. Um, so so remember that some of them are charged, some of them are going to undergo temporary covalent interactions with the substrate. And as you remember from organic chemistry, when you're looking at those mechanisms of organic chemistry, it has everything to do with like redistributing the electrons in order to make good leaving groups, for instance, or make something more easily ionizable, make it uh, do a nucleophilic attack onto the water next to it or something like that. These sorts of things are facilitated by the binding to the R groups of the coordinating amino acids in the active site. And the last thing is uh, creating a microchemical environment that is more conducive to the reaction. So remember that some of those coordinating amino acids are ionizable. And so maybe if it's a carboxylic acid, depending on the pKa of the active site, we might have it in the OH form or in the O minus form. And so that whether it's charged or not, it's going to change the chemistry that's going on inside of the active site. And so by holding the reactants in the proper orientation, stressing the bonds so that there's a conformation that more closely resembles the transition state, doing temporary covalent interactions and creating a microchemical environment that is conducive are the four ways that we lower the activation energy and speed up the reaction. Remember that we can only speed up the reaction, we cannot change the delta G. So if a reaction is unfavorable, it's going to stay unfavorable and it's going to require the input of energy. An endergonic reaction is an endergonic reaction whether there's enzyme there or not. So I also wanted to talk a little bit about what I mentioned earlier about pH and temperature. Um, so so when we look at the enzyme kinetics, we see this Michaelis-Menten curve um, shows us that as substrate concentration goes up, we approach some maximum velocity, and this maximum velocity, known as Vmax, is a line of the maximum velocity that the rate of reaction becomes asymptotic to. And that line represents when every single active site has substrate in it. So if it just makes sense that if there are no more active sites for substrate to bind to, then you can't continue to increase the rate of reaction. And so it makes a lot of sense why an increase of substrate is going to increase the rate of reaction and only up to some maximum rate of reaction. Um, and then the second important number to know is that when your rate of reaction is half of the maximum rate of reaction, the substrate concentration, the substrate concentration at which the rate of reaction is half maximal is known as the uh, um, Michaelis-Menten constant. And that constant is defined by um, the affinity of the substrate for the active site and the disaffinity of the product for the active site. And so the on rate and off rate of substrate and product, respectively, from that active site are going to define the Michaelis-Menten constant. So how are temperature and pH going to affect the rate of reaction? Well, um, if we try to imagine we're inside of this milieu, these uh, molecules are moving around with Brownian motion. So as we increase the average random molecular kinetic energy or increase the temperature, they're going to move faster. And if they're moving faster, the number of times that they collide with each other is going to go up. And so the substrate colliding with the active site, being able to find the active site and bind to it, is going to increase as temperature increases. But as temperature increases, remember that the protein structure is being held together by those R groups, as well as hydrogen bonding within the backbone, creating the secondary and tertiary structure, which we will talk about when we get to proteins. And so as you heat up the protein, maybe those hydrogen bonds get broken. If those hydrogen bonds get broken, then we're going to change the shape of the active site. And so this loss of activity with an increase of temperature is called denaturation. And that was the egg whites that I mentioned earlier. So how does pH affect um, rate of reaction? I, it is not correct to say that proteins work better at high pH, proteins work better at low pH, or proteins work better at neutral pH, because every protein has its optimal pH, and this has a lot to do with those coordinating amino acids in the active site. What their ionization state is going to have everything to do with with the pH of the milieu. And so, if you need a charge-charge interaction between a amino group on an amino acid, not the amino group, but like say it's arginine, and you've got some amino group that is going to interact with the substrate, but it only interacts when it's in the NH3 plus conformation. Then at at the wrong pKa, the wrong pH, the the ionization state might not be correct, and then you wouldn't have an interaction. And so each protein has its optimal pH. For instance, pepsin is only active in the acidic environment of the stomach. It becomes inactive when it enters into the um, intestine because of the increase of pH. I also demonstrated today the uh, um, competitive and non-competitive inhibitors. Just to recap, competitive inhibition is um, when the inhibitor binds to the active site, and so it competes with the substrate for that active site. So if the substrate is in great enough concentration, it can overcome a competitive inhibition. Um, and so competitive inhibitors are competing for the active site. Non-competitive inhibitors, however, bind somewhere else on the enzyme and cause an allosteric change in the structure of the enzyme, changing the shape of the active site. And um, and so you cannot compete off a non-competitive inhibitor. That is to say that no amount of increase of substrate is going to change whether the non-competitive inhibitor is inhibiting the enzyme, because it binds somewhere else other than the active site and changes the shape of the protein, which changes the shape of the active site. And last thing I want to talk about today, I want to talk about the uh, uh, the inhibition using the downstream product. So think about this biosynthetic pathway where um, B is the product of enzyme 1 and is the substrate for enzyme 2. And C is the product of enzyme 2 but is the substrate for enzyme 3. If we inhibited enzyme 2, there would be no C, no D, and a buildup of B. And so um, if we inhibit with the furthest downstream product, if D inhibits enzyme 1, then that will give us a good inhibition, because when D inhibits enzyme 1, then it would only do that if there was too much D. Then there wouldn't be any more B, there wouldn't be any more C, then there wouldn't be any more D, and that would relieve the inhibition. And so there's not toxic buildup of anything. It builds up at A, and usually when you have this scheme for feedback inhibition, whatever the first thing is some metabolite that is not toxic when built up. And so if there's no D, then enzyme 1 works perfectly, causing B, causing C, causing D, and then D inhibits enzyme 1, loss of B, loss of C, loss of D, and the inhibition is relieved. So, so that's the plan for feedback inhibition. So I hope that you understand that. If you didn't understand anything from any of these 3 videos, please come talk to me about it. In class, it's perfect time to get your class participation points, or come to my office during office hours, or really anytime. Just come to my office and let's talk about it. Okay.